Secure Cyber Resilient Engineering, SCRE, White Paper Series, System Engineering Benefits Cyber version 1.0, USDRNE, which stands for the Under Secretary of Defense for Research and Engineering. October 2024, prepared by the MITRE Corporation. I know this is really hard to see. You'll have to just bear with me, and maybe I can turn this into a YouTube short or something. But I found this on LinkedIn, somewhere I very rarely go, and the format is screwy here. Introduction. The System Security Directorate in the Office of the Under Secretary of Defense for Research and Engineering. If you love acronyms, here you go. OUSD, parentheses R&E, Science and Technology, S&T, Program Protection, S&T-PP, and then Office, which apparently gets left out of the acronym, is conducting a project to establish the practice for secure cyber resilient engineering, SCRE. And remember, this was October 2024, the white paper is dated. SCRE is the term used for the systems engineering practice that achieves the objectives of weapon system security and cyber resilience. The practice accounts for the adversity associated with the operational domains of air, land, maritime, space, and cyberspace, and adversity associated with the cyber-physical characteristics of weapon systems. The OUSD R&E project develops a series of white papers to acquire feedback from the weapons system community on technical aspects, informing the establishment of the practice. Establishing the practice is motivated by the absence of relevant codified engineering practice for trustworthy, secure, and resilient systems within the Department of Defense. The existing guidance for security, cyber resilience, cyber survivability, and all associated security and cybersecurity risk management, while suitable for organizations to manage operational risk, are not suitable for system design, implementation, and other parts of systems engineering practice for complex systems. Okay, so I would summarize that by just saying the existing guidance is not suitable. This is one of those sentences you could put into ChatGPT and see if it could break it down better. This shortfall extends beyond DoD to include the international community. The International Council on Systems Engineering, INCOSE, Systems Engineering Vision 2035, has recognized this by citing the need to have security as a foundational perspective, as performance and safety are now and working to achieve. The white paper discusses why systems engineering perspectives, concepts, activities are useful and benefit architecture and design efforts that achieve cybersecurity, cyber resilience, and cyber survivability objectives within foreseeable operational conditions. This white paper will be revised to capture evolving thought as the SCRE practice matures. To assist in maturing the contents of this white paper and the SCRE practice in general, please send comments to this email address. Background. This section discusses systems engineering and related topics with potential for benefiting security and the creation of secure systems. For this paper, a system is an arrangement of parts or elements that together exhibit a stated behavior or meaning that the individual constituents, like politicians' constituents, just kidding, do not. So the elements include all the associated equipment, facilities, material, computer programs, firmware, technical documentation. Oh wow, that is included. Services and personnel required for operations and support to the degree necessary for self-sufficient use in its intended environment. And I found the zoom in button. This paper defines security as freedom from those conditions that can cause the loss of assets. That is, items valued by a stakeholder, with unacceptable consequences. Unless otherwise noted, this paper will use the term security to refer to cybersecurity, resiliency, and survivability, as well as system security, resilience, survivability. Cybersecurity is viewed as pertaining to consequences of the loss of information's confidentiality, integrity, and availability. Cyber resilience is viewed as pertaining to the loss or degradation of capability associated with cyber resources. Cyber survivability is viewed as pertaining to loss or degradation of mission-related functions due to cyber events. As discussed in 3 essential characteristics of a secure system, I should have said footnote 4, so as discussed in footnote 4, 3 essential characteristics of a secure system are 1. It, as in the secure system, delivers the required system capability despite intentional and unintentional forms of adversity within foreseeable operating conditions. It enforces constraints to ensure that only the desired behaviors and outcomes associated with the required system capability are realized while satisfying the first characteristic. Number 3, it enforces constraints based on a set of rules to ensure that only authorized human-to-machine and machine-to-machine interactions and operations are allowed to occur while satisfying the second characteristic. To achieve these characteristics, each of and the relationships between the system capability, desired behaviors, desired outcomes, and the set of rules must be defined unambiguously. The characteristics are to be achieved and maintained within the requisite assurance. So number 8, and I wanted to see 4. So 4, note other SCRE products use the term cyber in a more restricted manner than as used in this paper. All right, so we're going to be really broad and holistic about the term in this paper. And then it says interpreting the term cyber was examined in depth within 39. So I guess we'll get there. Are these sections and not footnotes? We do not have a table of contents, so I can't tell you. So back to 8 up here, or section 2.1. What is systems engineering? It is a transdisciplinary. I was a systems engineer and I never heard this term. So it is a transdisciplinary and integrative discipline for enabling the successful realization, use, and retirement of engineered systems, using systems, principles, and concepts, and scientific, technological, and management methods. Consequently, systems engineering is dependent on other engineering, scientific, and social disciplines, performing a technical role to integrate them to effectively engineer successful systems. Section 9, and then page 32. Thus, systems engineering has a responsibility to understand the disciplines referred to as cyber, and how such disciplines interact with other disciplines such as reliability, availability, maintainability, and safety. And I'm used to seeing this as RMA. The systems engineering team interacts with stakeholders to understand all stakeholders' concerns, needs, constraints, and priorities to ensure they are expressed in system goals. So we have a figure, foundational relationships between system life cycle processes. This is from 4. So it's not section 4 because we were on section 2.1. So what am I missing? Let's go back because this was yet another comma. So the SE team interacts with stakeholders to understand all kinds of things, objectives and requirements is part of the purpose of that understanding. This understanding helps systems engineering optimize objectives to address stakeholder needs in the context of certainty and uncertainty. I like that. We don't just want objectives. We want optimized objectives. Well, systems engineering activities include a focus on a progressively deeper understanding of the interactions, sensitivities, and behaviors of the system, stakeholder needs, and its operational environment to inform optimization decisions among objectives. This focus is about increasing certainty and reducing uncertainty about the decisions while recognizing any decision will have uncertainty. The priorities across goals and objectives inform the focus. Systems engineering occurs within system life cycle processes through activities and tasks, described in ISO, IEC, and IEEE 15288:2023, as well as NCOSI's Systems Engineering Handbook and the Systems Engineering Book of Knowledge. The processes occur concurrently, iteratively, and recursively to achieve deeper understanding, increased certainty, and reduced uncertainty, while realizing, supporting, and evolving the system. Figure 1 shows the life cycle processes and foundational relationships. Top left starts with agreement processes, acquisition, supply, entire box feeds into these other two technical management processes. Technical processes, over here, organization, project, enabling processes. Okay, anybody who loves systems engineering can pause here and read through the boxes. In this paper, the processes and the underlying activities and tasks performed in support of the processes represented in Figure 1 are the full context for Section 2, Point 2, emergence, behaviors, and outcomes resulting from how the system is composed. Section 2.3, systems thinking, considering the connected whole. 2.4, assurance grounds for justified confidence a claim has been or will be achieved. Section 3, securities system considerations, except for Section 3.3, which focuses on the subcontext represented by the set of design loop activities, which we can see in Figure 2 below. So 3.1 is security is a system problem. 3.2 is a system may be weaker than its weakest link. That's cool. And then 4. So we go 3, 1, 3, 2, 3, 4. Where's 3, 3? Oh, okay, 3, 3, right? It's killing me that it's not down here. But anyways, 3.4. Security engineering is part of systems engineering. Section 4, controlling behavior and outcomes. Though the discussion in the section focuses to the activities represented in Figure 2 below. And then Section 5, stakeholder engagement. Though the discussion focuses to the subcontext in the sections, Figure 3. So we have design input requirements and other supporting information, system requirements definition, system analysis, architecture definition, design definition, verification. And this is SCRE, execution for system design. Additional information on systems engineering can be found in the following resources: Systems Engineering's roles, responsibilities, and activities and tasks within the system lifecycle. Processes are described in 3.10.11. See also the National Aeronautics and Space Administration System Engineering Handbook. All right, I love the NIST special publications. So 800-160 Volume 1, Revision 1, Appendices G through K discusses security considerations for systems engineering roles and all that stuff. Section 2.2, emergence, refers to those behaviors and outcomes resulting from how individual system elements compose to form the system. The definition of a system makes it clear that emergence produces behaviors and outcomes of the system that cannot be produced solely by the individual elements that comprise the system. Wow, of course. So therefore, emergent behavior and outcomes are necessary to achieve a system's purpose as expressed by the requirements that define the system. However, a system may also produce emergent behavior and outcomes that its requirements do not specify. Any unspecified behavior and outcome must be 1. Treated as being unintended, that is, consistent with the system requirements, and 2. Assessed as risk, because uncertainty is a contributor to risk. Decision-making for the response to unintended emergent behavior and outcomes requires acquiring an understanding of the range of unspecified behavior and outcomes that span those that are desirable, i.e. beneficial, productive, to those that are undesirable, harmful, or not productive. Now, the system requirements may then be revised to explicitly include or exclude the unspecified but desirable behavior and outcomes, and revised to protect against the unspecified and undesirable behaviors and outcomes. And that whole process, if you ever have a chance to be a part of, is pretty fun. This activity is repeated to address emergence that results from design decisions as the design is matured for implementation. Emergence is a complex system characteristic that is necessary for the system to fulfill its specified purpose. It is also a source of uncertainty that contributes to risk and can be harmful. Because the system includes the machine, the human, and the environment, the system behavior and outcomes can change at any time in the system lifecycle due to any combination of machine, human, or environmental behavior, behavioral, and outcome changes. This drives the need for comprehensive system analysis to inform decisions for effective control to ensure emergent behavior and outcomes are as intended as determined by the system requirements. For more on emergence in a security context, see section 3.2. And this. I'm going to end the video here. In the next one, we'll start with section 2.3, systems thinking.